Good day, statisticians. Today we're going to talk about a two-sample t-test for the difference between two means. And again, now we're doing a t-test. Why are we doing a t-test and not some kind of z-test? Well, remember, there's really only one reason we'll ever do a t-test instead of a z-test, and it has to do with sigma. Of course, what does sigma stand for? It is the population. This is the population standard deviation, right? And if you don't know this, right, if this is you right here, and you're like this happy little person, and you're like wondering what the heck is the population standard deviation, and you don't know what it is, then what can you do? Well, you'll just take a sample, right? So here's your population, here's the population, and you'll take some sample from that population, and you can calculate a sample mean and a sample standard deviation, and using that sample mean and that sample standard deviation, you will be able to do your two-sample t-test. So hooray! So let's kind of see what's going on here in terms of some examples, but the key thing here is, of course, what will be the standard error formula when we're doing this. A lot of the math we've been doing with all these tests is essentially the same. The key here for the t-test is what will be, first, our test statistic. So, of course, our test statistic will be a t, and what will be our formula? Well, what we're going to do is we're going to take a sample from some population, right? So in this case, to do a two-sample t-test, there'll be two populations, right? Here's a population, here's another population. And from this other population, we'll take another sample mean and another sample standard deviation. We could call this 2, and then we could call this guy 1, right? And so for our test statistic, we're going to take the difference between our two sample means, and we expect that difference to be negligible. You'll see, we'll expect that difference to be 0, right? And so that will be the numerator, and then the denominator will be the standard error formula in this case. And we'll see that the standard error formula will be something very standard. In this case, for a two-sample t procedure, whether it actually ends up being a t-test or a t-interval, and we'll do a t-interval in another video, we have this formula right here, which again is just like the population, the sampling distribution standard deviation formula. But of course, this is standard error, so let me use the correct notation. We have the standard error of the sample mean. And if you took a sample standard deviation divided by root n, of course, if you squared that guy, then that becomes the variance, right? And then when we square this, you get that guy squared, and of course, the square of the square root of n just becomes s squared over n. And so we're adding the variances here, and so that's what we'll have here. We'll take the big square root of s1 squared over n1 plus s2 squared over n2, and that'll be our test statistic. The other interesting thing that we're going to see here is going to have to do with the degree of freedom. Some crazy stuff goes on with the degree of freedom here. Remember, in the past, whenever we had just one sample, when we did a one-sample procedure, one sample, then the degree of freedom was simply n minus 1 for a one-sample t-test or a one-sample t-interval. We're going to see when we go to two samples, when we're at two samples, right? In other words, that we're taking two sample means from two separate populations, the degree of freedom gets crazy. We're going to have some crazy stuff going on there. And so I'm not going to show you that right now, but just anticipate that's going to happen. All right, let's do an example with the basics of the math. Again, we're not going to do the full 4-step process here. We're just going to make sure we have the key math down for doing a two-sample t-test. So let's look at an example here. Let's suppose you are comparing the duration of time it takes for two different varieties of paint to dry to the touch, right? So it's not all the way dry, it's just right at the touch. You collect data from 35 random samples. So, okay, so there's 35 samples where you painted surfaces, I guess, right, of each type of paint, and you find the following data. So here we have two types, and this is the amount of time it took for that paint to be dry to the touch, which doesn't mean that it's all the way dry, it just means you could touch it, you're not gonna get paint on your hands, right? So 68.1 minutes on average here, 63.7 minutes on average here, and then we have standard deviations. They actually ended up being kind of similar. They both had a standard deviation of 8.4 minutes. So a decent amount of variation away from the mean here. And the question, is this significant evidence of a difference in the mean dry to touch times of these paints? All right, so if I'm just looking for evidence of a difference, that would mean that my null hypothesis, right, is going to simply be that the average dry time of these two paints is going to be the same, right? So I'm going to say the mean of type 1 would be equal to the mean of type 2. And as we saw with proportions, we're going to end up writing this as a difference. That would mean that the mean of type 1 minus the mean of type 2 should equal 0. The alternative will be the mean of type 1 and the mean of type 2. Well, what's the only thing? We're only trying to see if there is a difference. And it's just saying that there is a difference means not the same, so we'll say not equals. And so then, of course, we'll say that mu1 minus mu2 is not equal to 0 will be our alternative. Technically speaking, we should define what mu is, but again, I'm not doing the full 4-step process. I'm just trying to get down to the core ideas here. Okay, so how do we proceed here? Well, let's take a look at our sample data. And one nice thing that, just as an aside, one nice thing that we see here that will allow us to use the t procedures is we have fairly large sample size of 35. Since that's over 30, we can use the large sample condition to use t procedures in this scenario, right? If sample size was less than 30, then I would need to make sure that either the population itself was normal or that these sample distributions didn't have any significant skewness or outliers. But in this instance, we can go ahead and calculate our test statistic. So, okay, our test statistic would be a t-test statistic. And so what I'll do is I'll take the difference in my sample means. So that'd be 60, in this case I'm doing mu1 minus mu2. So I'll do 68.1 minus 63.7, right? And of course, I assume that that difference is 0. So I could subtract 0 just to be like thorough with a formula, but it's not really all that important. We could always test hypotheses the difference is some number other than 0, but in AP Stat we don't do that. So there you go. All right, so we have the difference between the two sample means as our numerator, and then the denominator is going to be a big square root, right? Remember, we're working with this formula here. We'll take the square root of the sum of the variances of each of the separate standard error formulas. And so in this case, I could take the 8.4, and I will square that. And I'll divide that by the sample size. Now, both of these were 35, so we don't have to have the same sample size to do these procedures, but in this case, we just happen to. So I'll do 35 for both, and then this was 8.1 squared. And so now I'll just go ahead and calculate this guy, and I'll get, all right, let me plug it into my calculator. I do 68.1 minus 63.7, whoops. Forgot the minus sign, 68.1 minus 63.7. I'll divide, so I subtract that, and I'll divide by, all right, a big old square root. That was 8.4 squared divided by 35 plus 8.1 squared divided by 35. I don't remember where I got that squared thing. I got it from, I think I saw someone saying it on a YouTube or something, and I probably just stole it, but I don't know, I like to say squared for some reason. So this guy, 2.2307 is our test statistic, right? Now, here's that other dimension, that if I want to calculate a p-value, I need to know which t-distribution to use. Because if you recall with t-distributions, t-distribution doesn't describe just a single shape, like the normal curve has certain proportions that are within a number of standard deviations of the mean. The t-distribution actually evolves in shape depending on the degree of freedom, right? So let me get another piece of paper real quick. So as a reminder, right, if you had a degree of freedom of like, say, 2, you're going to end up having a t-distribution that's like really, really, really low in the middle and then fat on the edges. While if the degree of freedom went way up, right? So let's say we had a higher degree of freedom, then so this is like a degree of freedom. I mean, this is obviously not to scale, but this is a degree of freedom of, say, like 30. Now, all of a sudden, you've got something that's taller and narrow on the edges. And we also said that as the degree of freedom approaches infinity, then this t-distribution is going to approach the z-distribution. In other words, the t-distribution would become the normal distribution. So the key here, that if I want to actually calculate a p-value, right, and if I take a look and I say 2.2307, say here's 0, and here's 2.2307, and I go like this, and then I go, since this was a two-tailed test, I put negative 2.2307 over here. If I was to shade this business in, there's going to be a different amount shaded in depending on which t-distribution I'm looking at, right? If the degree of freedom was really, really tiny, then this would be actually a much higher proportion out on these edges versus if the degree of freedom was something much larger. So it's essential to calculating the p-value to know what the correct degree of freedom is. So actually, we're going to see that there's two approaches. There's kind of like the truth, and then there's what we do if we don't have fancy technology, right? So what's the degree of freedom for a two-sample t-test? Well, I wrote this out. There's two two scenarios, right? First, there's the conservative scenario. This has nothing to do about being liberal or conservative politically. This is all about what's safe and what's not safe. So the degree of freedom for two sample t procedures, and this will be the same for a t-test or a t-interval, is always going to be, in a conservative approach, either the smaller of n minus 1 or n minus 2. So in this cases, we actually had the exact same n. In both scenarios, we had n1 and n2 were both n1 was equal to n2, and they were both equal to 35. And so if we used the conservative approach, right, then that would mean our degree of freedom would simply be 34. And we could go ahead and use that, right? Now, there's actually a truer approach for the degree of freedom. It comes from this rather elaborate formula, right? And it's kind of neat. If you, it comes up with the degree of freedom that's related to thinking about the relationship between sample sizes and standard deviations. This formula, good news, you don't need to memorize this formula, right? So if you're sitting here right now, your eyes are glassed over and you're saying, holy cow, like what is going on? You're expecting me to hold this whole thing in my head and I need to have this memorized? Guess what? This formula is not even on the formula sheet for the AP exam, and that's because you can just trust your calculator to do the whole thing for you. The calculator knows this formula and it will use this formula if it calculates a particular degree of freedom, right? And so the good news is that if we wanted to come up with the p-value here, if you just use the calculator's functions, and we'll look at that in a minute, if you hit stat tests and you go down to, this will end up being a two-sample t-test, option number 4 there on my TI 84 plus CE calculator. That's what we could use, but otherwise, if you don't, for some reason you don't have the TI-84, you just have some other calculator that does T stuff, which I'm sure you don't. I mean, you're going to have this calculator no matter what. You can just use this conservative approach. And we'll calculate it both ways just so you see. So in other words, if I go back here and I want to calculate this test statistic, if I use the conservative approach, and if I'm using the conservative approach, I'm going to write that down on a piece of paper. So I would say the p-value, given the degree of freedom equals 34, right? That would be a conservative approach, right? Is going to equal, let's see here, I could plug this in my calculator and now I could go to, just like we have normal CDF, we got a TCDF here. So I'll go down to TCDF and I'll say my test statistic was 2.2307. So I do 2.2307 to infinity, some very, very large number. And my degree of freedom, if I use the conservative approach, is 34. I'll hit paste and enter, and shazam, I got 1.62. Now, of course, since this is a two-tailed test, I will double that. And so I got a p-value of 3.24%, right? 3.24%. And so say I had a 5% level of significance, I would reject. At 1% level of significance, I would fail to reject. Good times, right? All right, so that's how I would get the p-value if I did it by hand using this conservative approach to the degree of freedom. Now, if I want to get the actual degree of freedom that's most useful here, then I could just go and do the two-sample t-test in the calculator. Oops. So if I go to tests, I go down to two-sample t-test, I hit enter, stats, I can put in the information. Actually, I think, oh, look at that. I already have this in from earlier today. Let me make sure that I have it in right. Yeah, that's all in there. Now, notice this calculator asks you something about pooling. We actually talked about pooling when we were doing the two-sample z-test for proportions, and we had some pooling going on there. But let me give you a quick hint. If your calculator asks you to pool, the answer is no. No. In AP Stat, we won't pool. In fact, at the end of my next video on confidence intervals, I'll actually explain what that pooling means. But if the calculator says, do you want to pool? The answer is no. Do you want someone to pee in your pool? No. So don't get your p-value from pool data when it comes to a mean. No peeing in the pool. That's terrible. All right. So hit calculate and look at this. Now, what do we have? This time we actually got a p-value that is a little bit less. The same test statistic, 2.2307, but the p-value went down. It went down to 2.9%, right? And so the p-value, this is the better p-value. The p-value, given that we had a degree of freedom of something else, like what was we'll see what it was in just a second, will end up equaling 0.029, right? Or 2.9% essentially, right? So we ended up having a smaller p-value. What was the degree of freedom? Well, notice the calculator came up with 67.91. Okay, that's nice. 67.91. How did it come up? Notice it's a decimal degree of freedom too, which means like, what does degree of freedom even mean? It's like the first time you put in your do you ever do this? This is just as an aside. Do you ever put in your calculator 0.5 factorial? If you go over here, let's see, if you go to 0.5 factorial, you're like, wait, 0.5 factorial, that doesn't even make any sense. Oh, but it is a number. Look at that, crazy, right? So, there's all kinds of things that have different interpretations with discrete numbers than they do with continuous, but it is possible. So it is possible to have a decimal degree of freedom, and that's actually what we have here. Just as a fun aside, notice that actually 67.4 is actually kind of, there's a way to think about these sample sizes and how it's kind of connected, right? 35, what if you, say, for instance, added 35 plus 35? What would you get? 70. That's starting to get close to this degree of freedom. There's actually something really cool that happens in a special case scenario with this formula that I will explore at the end of another video. But anyway, here's the key idea. With that this formula suggests that we actually have a higher degree of freedom than we think. So the conservative approach will always end up giving us a p-value that's over what we would get if we used the true, right? So the conservative approach is conservative because it's trying to it's not going to ever say that our p-value is lower than it really should be. This is what our true p-value should be for this scenario if we're using the true degree of freedom that we can get away with. But again, if for some reason you don't know that, then the safe bet so that your p-value isn't smaller than you would count, than you might estimate, is to just use this conservative approach of n1 or n1 minus 1 or n2 minus 2. So there's the key idea. Again, if you really just want to do this test, the best way is to just do it in your calculator. It's going to give you the best evidence for the two-sample t-test. It's going to use the correct degree of freedom. You don't have to do any fancy calculating. Don't pee in the pool, and life will be good, and there you go. So there's the core idea, friends. I hope this helps you. Hope you have a beautiful day, and you'll see me in another video talking about the confidence interval. Catch you on the flip side.